Okay, thank you everybody for joining us. We are very happy today to have Patricia Ning from Texas A&M, along with our guest panelist Edward Ionides, and she will be presenting a paper on high-dimensional parameter learning. I'd just like to remind everybody that we have a workshop coming up. The deadline is on the 15th, so please make sure that you don't miss the deadline. The workshop is for young researchers, junior researchers, and early and PhD students. So without further ado, Patricia, the floor is yours.
Okay, thank you so much for the introduction and the opportunity to present my work. In this work, we conduct high-dimensional parameter learning over the nonlinear, non-Gaussian time series data. Specifically, what I mean is the spatial temporal data with network involved. And this work is based on the paper. It's called the Iterated block particle filter for high-dimensional parameter learning, and it can beat the curse dimensionality. This work is publicly available in arXiv and is currently in revision at the Journal of Machine Learning Research. It's a joint work with my postdoc mentor, Edward Ionides. He's also here today. Next. Oh, why I cannot? Let me try again. Okay. Seems like I have some issue. Probably like this. Okay, it works now. Okay, can you see it? It's okay, like this way?
Yes.
Yeah.
Okay. Or maybe let me try again the full screen. Oh, it works now. Okay, sometimes there is technical issues. And for the spatial temporal data, it has the dependence in the time dimension and also dependence in the spatial dimension. This kind of data is a very hard to handle time series data. This is one of the most hardest type in time series. But this kind of data is inevitable because in nowadays we can, for example, the case of the COVID, it's so far we already have a 6.8 million deaths worldwide. And even the last 24 hours, there is 209,000 cases, new cases. So it affects everybody's life so far, and it has lasted quite long. It's the data changing every day, and it's changing across so many locations all over the world. And we have to analyze this kind of spatial temporal data. This kind of data is kind of tricky because it's not only just monthly available. Sometimes it's for some places, it's daily data. So we have the data increase every day. And you can imagine, for example, it's 100 cities. And even just 10 days, there's already 100 times 10 as 1,000 data points. So it's quite a high dimensional. This dimensional can be understood by the time dimension and the spatial dimension in this kind of sense, high dimension. And we consider it's a nonlinear, non-Gaussian case. This is to model the spatial temporal disease transmission systems. This kind of system have this kind of characteristics. And it's stochastic and imperfectly observable. Spatial temporal inference for the epidemiological and ecological systems is arguably the last remaining open problem from the 6 challenges in time series analysis of nonlinear systems by one earlier study published in Science. A disease transmission system is stochastic and imperfectly observable. Thus, it is commonly modeled by a state space model. State space model also being called is a hidden Markov model, or it's called is a partially observed Markov decision model. We consider an extended state space model here. The latent state Xn is a Markov chain taking values in a general Polish state space X. So in this work, we consider it's a very general state space, the Polish state space. The mathematical definition is separable, completely measureable topological space. It's a long term, and it's very general. It covers all the spaces we are familiar with, like a real space, and a complex valued, and discrete valued, and real valued. And also it covers the manifold. It can be finite dimensional or infinite dimensional. So here, for each state, we already covered the infinite dimensional analysis. And we allow this state space has its general reference measure. The observation sequence Yn is conditionally independent given this latent state, Xn. And it takes values also in a general Polish state space. So that means my observation sequence can be very high dimensional or infinite dimensional. Given another one is high dimensional or infinite dimensional. Recently, I attended some talks. It's named deep Gaussian process. And in our case, absolutely we already covered that. And also we attended this to the infinite dimensional case, infinite layers. You can think that way. And also we allow the Polish space with a general reference measure. We also, besides these two, we also consider there is a Markov chain theta n. This theta n is just for the parameter learning purpose. The classical state space model only has the Xn and Yn. Here, our theta n is for the parameter learning purpose. We also allow it to have a very general state space and a very general reference measure. Our extended
Patricia, sorry,
yes?
just a quick question. What do you mean by reference measure? Is that like a transition probabilities for?
Reference measure is like, let's just think the real valued space R. R, the reference measure is usually the Lebesgue measure. Or you can see it's like others, if you think any probability space, the reference measure you can think is the probability measure.
Okay, okay.
Yes.
Okay, got it. Thanks.
And our extended state space Xn, Yn given theta n also has a general transition density. Let's focus on just the theta n. If we have a fixed theta n, this is like the standard, the classical state space model. Firstly, we have the transition dynamics with the latent state. It's a Markov process, Markov chain. That means the Markov property means today's value only depends on yesterday, but not the other days before that. And there is another density. It's Yn given Xn. This is the data given the latent state this way. And this is the reference measures, is what I mean. And then this is the transition density given theta n for each value theta n. A model that is defined using a simulator instead of an analytically tractable characterization of an underlying process is said to be implicitly defined. So this kind of model is quite general, especially it's with the spatial temporal modeling. If you have an interacting particle like a system of model, even just the partial model, for example, the dynamic over just one vertex, even that is Gaussian, like a normal distributed, even just that. But there is it's nonlinear model with interaction over these dynamics, each vertex dynamics. We still have no idea what is the general distribution of the whole model. So this kind of model is the models of the complex dynamical systems are sometimes defined implicitly by a computer simulation algorithm, which lacks analytically tractable transition density. That means for this kind of complicated model, we have no idea of the general transition density, but we can use the computer simulation to simulate it like that. This plot is an illustration of the time inhomogeneous transition density. Time inhomogeneous transition, it means today's transition density is different to any other days. It can be different or can be the same. If all the days are the same, it's called time homogeneous. If I allow each day to have its own transition density, like for example, here for each one, it has index n under n minus 1, like that. If each day is allowed to be different, this is called time inhomogeneous. This structure is, I have my Markov chain transition, the dynamics. And for the theta n, this one contributed to xn, and together they contribute to yn, n minus 1. Theta n minus 1 go to xn, and then xn minus 1. This is the time inhomogeneous setting, so it's quite general. The state of the xn, yn, theta n, and each time n is a random field. xn way, yn way, theta n way. V here means it's a vertex in the vertex set, capital V. This is indexed by a large graph, G, with V as its set of vertices and E as the set of edges. So we consider a very general graph. The only assumption we assume of this undirected graph is the partition. It's called non-overlapping partition. That is, we partition the vertex set into non-overlapping blocks. So as long as there is no overlapping with these blocks, we are good. Any kind of partition is okay. So for example, in this illustration here, I have 1 and 2 vertices in the block 1, 3 and 4 in another block, 5 and 6 in one block, 7 and 8 in another block. Or we can partition in another way, like 1, 2, 3, one block, 4, 5, 6, another one, 7 and 8, one block. So that means as long as it's non-overlapping, we are good. And we consider is the R neighborhood interaction. That is, for each vertex, it only interacts with its neighbors in the range of R. R can be any number. It's very realistic in the graph theory analysis. For example, I got COVID and I'm currently in the United States. I only interact with people in the United States, but never people in the Europe. That's what it means. And for this finite range interaction, this model is quite similar. Actually, I got this plot is from the graph neural network. This is very similar to the message parsing in their setting. And later, as I talk about this work, you will see more similarity with the graph neural network. Okay. And for this finite range interaction, this also involved in the transition density. So before I mentioned that this is a Markov model, not only that, here if I under yesterday's value, so this is a value of today with vertex V. I give it all the values of yesterday, the whole graph. However, I only consider it the vertex that it has I have interaction with. For example, today, my value today only affected, only conditional on the people of the United States of yesterday, like this. Only the neighborhood I interact with and yesterday's data. So it's like this. So as long as xn minus 1 in the neighborhood V equal to x bar, another value of yesterday in the neighborhood V. As long as these two are the same, the transition density is the same. So this is a model assumption, very realistic. And also I assume the same to the theta n, like that, the Markov chain for parameter learning purpose. So let's see the graphical Statespace model structure. The structure, let's focus on this x, n, I. N means is a time dimension. I means vertex I. For this one, if I only consider one neighborhood interaction with R equal to 1, that means this data only depend on the last day, n-1, and vertex I itself, and its neighbor, I-1, I+1. So this is the structure. And for each vertex, it contributed to the observation in that day and that vertex. So this is the model structure.
Sorry,
yes.
Patricia, how you define neighborhood?
The
for
neighborhood
the implementation
definition
here.
Yeah, this is the standard graph
right.
theory definition. That means I draw a circle. The radius of the circle is R. If I focus on V, so all the neighbors in the circle is I call it neighborhood.
Okay, so how you define R? How we can define R in practice?
In practice, it does not really matter, but here is for the theoretical analysis purpose.
Okay.
Okay. In real life, it can be any number as long as it's finite.
But I guess
we will see. Yeah,
okay,
we will see in the
that.
algorithm, it does not show up, but in the analysis, theoretical analysis, it showed up.
Okay, thank you.
Okay. And the algorithm we focus on belongs to the particle filter algorithms. It's also called the Bootstrap particle filter algorithms. This algorithm is also being called a sequential Monte Carlo. It's already been widely used in so many areas. It's a very classical algorithm, sequential Monte Carlo. It has its evolutionary analog. So firstly, we have the mutation and goes to fitness, and then we have the natural selection to have who left, who be diminished. And the Bootstrap particle filter algorithm is quite similar. So firstly, we initialize the model and the parameters, initialization. Then we predict based on the stochastic dynamics. When the new data comes in, we re-weight. We give it a weight, and based on this measurement. Based on this weight, we conduct a resampling. And after one day finished, we go to the next day. So it's totally a recursive scheme. The Bootstrap particle filter algorithm is widely used, but there is some issues. The issue is it has the curse of dimensionality, which means if the dimension goes high, the filtering performance will go down exponentially. So it goes down really fast, the performance. Therefore, in recent years, there is another algorithm being proposed. So this algorithm is called a block particle filter algorithm. The idea of this algorithm is that, if you think there is a cursive dimensionality over the bigger graph, the high spatial dimension, but it's okay with the small sized one. What if we conduct the partition and only consider a small block in this parallelized setting, and then we combine everything together, go to the next round. If this can be beat the curse dimensionality. So, and this idea, there is a block particle filter algorithm, and it really been showed this can really beat the curse of dimensionality. So the idea is, firstly, we still initialize the model and parameter. Then we predict based on the stochastic dynamics. Now, as the data comes in, the data we consider is in each blocks. In each block, we calculate its weight. And based on this block-wise weight, we conduct a resampling. When everything is done, we combine all the results together and go to the next day. So it's still recursive, but right now we already can do it parallelize it. So it not only can beat the curse dimensionality, and it also can save the computational cost, can reduce that. Based on the block particle filter algorithm, I developed the iterated block particle filter algorithm. This algorithm is for parameter learning purpose. And the block particle filter algorithm can only infer the latent state. but my algorithm can do both, but we mainly focus on the parameter inference. So at the beginning, we still initialize model and parameter, then we go to the perturbation stage of the parameters and the prediction of the based on the stochastic dynamics of the latent state. When data comes in, we consider data in each block and resample based on the weight in each block, calculated in each block. Here, not only we resample the state, we also resample the parameters. Then we combine everything together, go to the next day. Here, we also use the data cloning technique. For example, my spatial data, I'm good, but the time data is quite short. There is some biology examples on this. That means we only have, for example, only 10 time series data, but we have is 100 in the spatial dimension. In this case, we can replicate our data to be the next round and conduct the model training by this loop of data. So we loop each round of data. This is gives me the M iteration. Yes.
Sorry, but here you have to decide about the block size, right?
Yes, I need to decide the block size.
There's like a sort of bandwidth here, or
yes.
Like,
for example, the let me show you this one. Here, the block size, each one is 2. You can make it to be like a 1, 2, 3 a block, then the block size will be 3.
But so do you have a way to select that size or the size of the?
Oh, you can decide the size by yourself. For example, with the COVID data, I can decide by California, by state, and by New York state. California is one block, New York is another block, Texas is another block, like that. There's some spatial
so you take the whole
association.
state, okay.
Yeah, you can assign the blocks by your own performance preference.
Yeah. So Patricia, that's going to be critical for whether this actually works, right? Whether there's a block that is small enough to be computationally tractable and large enough to make an approximation of the type you need.
Yes,
Yeah.
Okay.
Yeah.
And the existing algorithms for parameter learning, there are 2 algorithms as a mainstream algorithm. The first type is 2 iterated filtering, I denote as IF approaches based on the particle filter algorithm. The IF1 is by my mentor, Edward, and published in PNAS, Proceedings of National Academy of Science. And then later in the year 2015, they published an improved version, also published and PNAS. We call it IF2. The key things about the particle filter is it is capable of handling the highly nonlinear latent processes, but it suffers from the rapid deterioration in performance as the model dimension increase. And these characteristics about the particle filter also carried to the algorithms for parameter learning, but based on the particle filter algorithm. So it carried to there. Another algorithm published in recent years and science is called Iterated Ensemble Common Filter Algorithm, IEKF in short. This is based on the Ensemble Common Filter algorithm. The key things about ENKF similarly is also carried to the IEKF algorithm. The good side is it's computationally scalable to high dimension, but it can be ineffective for highly nonlinear, non-Gaussian systems. So we can see these 2 algorithms. The first type is can handle nonlinear, non-Gaussian, but does not grow well with the dimension. The second type is it's scalable to high dimension, but it's not work really well with the highly nonlinear, non-Gaussian systems. So my algorithm is IBPF algorithm. This one and the later another one is we conducted some generalization and also conducted empirical analysis. This one already published. It's faster, already published, and Statistical Sinica. This is an algorithm that is generically applicable over partially observed, highly nonlinear stochastic spatial temporal processes, and able to beat the curse dimensionality. So let me explain the connections and difference to other popular algorithms. When there is no partition in the graph, the IBPF is IF2. That is because IBPF is based on the BPF, and IF2 is based on the particle filter PF, and the BPF is the block-wise particle filter algorithm. Next, when there is no parameter variable involved and no partition in the graph, no iteration, so IBPF is the particle filter algorithm. On that, if we add on the graph partition, it is a block particle filter algorithm. When there is no partition in the graph and no time involved, the IBPF is the iterated importance sampling. As I mentioned before, with the M iteration, this is called the data cloning technique. In nature, the IBPF is an IF algorithm, which generalizes the data cloning method based on the observation that iterates a base map, converges to a point mass, and the MLE, maximum likelihood estimate. To be specific, the same set of data, Y1 to Yn, capital N, is used in any of the M iterations of the IBPF algorithm, giving the result of the M's iteration. Next one, the initial value is the last one's output. So the M iterations output is the initial value input of the M+1 iteration. So we can see that all M iterations together can be represented as a filtering problem on M iterations of the data as follows. So we replace the data M times. The joint density of the classical state space model, we also call it a partially observed Markov process. It's the same thing. Can be written as this one. This is the joint density, which means I have the transition density and the emission density multiplied together for all the time steps. So we write this the Fy1 to capital N as a marginal density of the data. Then the likelihood function is defined by this way. This is the marginal of density of the data. And the MLE is a value that maximizes this likelihood. Here, remember we have the theta 1 from the theta series, from theta 0 to theta n. For this one, we have it's called its extended likelihood function, because we already imported its theta 0, theta 1, theta 2, capital theta capital N here. So let's firstly illustrate the model performance. With this spatial temporal data, we consider the measles data in England. It's in the year 1915 to the year 1965. It's a bi-weekly data of 15 years. And on the y-axis is the dimension of the cities. We numbered the cities by its size. For example, the first one is London, and the second one up to the 40th one. Cities in London. So this is city 1, city 2, city 3, go to city 10, go to city 20, city 40, 30, city 40, like this. This is the biweekly data of measles. We consider it the generalized spatial temporal modeling. So in this modeling, we consider it the SERR model. This is a very classical epidemiology model. So B stands for birth, and the SERR, and D stands for death. This SERR model, not only the general one, we consider each vertex has its own SERR model. This in epidemiology, this is called a meta population model. We consider it a time inhomogeneous case. That means the transition rate is depending on t. For each day, the transition rate can be different. Not only that, we consider it an interacting system. That means the transition rate can depend on the value of another vertex, not just these two. For example, the transition rate RSE between susceptible to exposed. This rate depending on time t and the value of how many people of R infected, like that. So the transition process is a jumping process. It's modeled by a negative binomial death process, according to some research of Edward and his student Bretto, published in the Annals of Applied Statistics. And also by Edward and his student published in the stochastic process and its applications. So we consider there is a rate of vertex V, the transition rate from S to E at the time t of vertex V is given by this formula. So in this formula, there is a gamma process here. This is a rate with a gamma process. This gamma process has mean t and variance sigma SET. So sigma SE I highlighted with red color. That means this is a parameter I'm going to infer. And batch VT is another parameter based on time t and for vertex V. So it's a spatial temporal setting the parameter. So this one models the school terms or vacation, the seasonal term. And here is the important parameter. This is R0V. R0 is one of the very important parameters in epidemiology. This is the annual average basic reproductive ratio. R0 is very important because it related to many of the important quantities in epidemiology, the transmission rate. And here, besides these two parameters, I also interested in this very challenging one, this exponential parameter. You can see here, there is a spatial interaction. For each vertex, it also related to the other vertex. For example, in some of its neighborhood, or somebody in its interaction weights, the other location's value. So here, I want to infer not only alpha bar V, also the alpha bar with the V2. So with this challenging inference, I cut it to be 4 cases. In the first case, I only infer the initial values of this transition dynamic, but for each location V. And for the second case, I increase the difficulty. Besides these initial values, I also infer the R0V. And the third case is I try a challenging one. Besides the initial values, I infer the exponential parameter. So this is highly nonlinear because it's exponential parameter. The first one is, I do it the most challenging case. I infer all these parameters together. So in the case 4, there are 7 parameters for each location. So if I just have 5 locations, 5 cities, there's already 7 times 5, 35 parameters to infer. So it grows with the dimension of the spatial dimension. So and the first one, this is the first case, only infer the four initial values for each city, So this is a city-specific parameter inference. In this case, I can see I compare with the INTF algorithm, and INTF used the ENTF, ensemble common filter. And it has its own metrics in the maximize MLE. And the second one I compare is the IF2 algorithm. IF2 algorithm is based on the particle filter algorithm, and it has its own metric of MLE. And then it's my own BPF metric in MLE analysis. So we can see in this data analysis, all the algorithms perform really well, as good as the true value. So this is a simulated data. We want to compare with the true value, the likelihood generated by the true value. We can see with the ENKF metric and the BPF metric. So all these algorithms perform equally well, as good as the true value. But with the particle filter algorithm, you can see it's not stable. All the algorithms goes down. So this means from this example, we can see two things. Firstly, is the particle filter algorithm metric is not reliable. We know that it has the curse dimensionality. So this is quite as expected. And the ENKF metric and the BPF metric, these two metrics are reliable. It's reliable. We can use that. So another fact we can learn from this data analysis is we coded all the algorithms correctly. Because we want to compare with the other algorithm, we have to make sure we coded our own algorithm correctly, but also others' algorithm correctly. So this is one demonstration on that. Now we increase the difficulty in parameter learning. We add on the important parameter R0. The situation is getting interesting. We already can see from the ENKF metric and the BPF metric, the performance of my mentor's algorithm IF2 is already goes down fast from with ENKF. It goes down from just the 4 cities because this is spatial temporal data. Even just the 4 cities, adding on the time dimension is already quite high because we have the bi-weekly data of 15 years. And with the BPF metric, the performance of IF2 goes down from city of 6. And INKF and our IBPF perform equally well, as good as the true parameters. In the third case, we increase the parameter learning difficulty by inferring the initial values and the highly nonlinear non-Gaussian one, alpha weight for each city weight. So we can see here it's already quite clear. The IETF really does not work well with the highly nonlinear non-Gaussian situation. If it's not highly nonlinear non-Gaussian, it might work well because it has a approximately Gaussian setting. It can work well sometimes, but with a highly nonlinear non-Gaussian, it does not work well. We can see the performance of it is really bad. It's quite low. Seems like the IF2 is not really bad. You can see it only lower a little bit, but actually it's just because the IENKF is quite low. How actually the IF2 also goes down fast, but it seems not that bad. It's just because of the range is high now, because the IENKF is really bad. For the most challenging situation, here we can see IENKF disappear because it's too bad performance to be drawn on the same plot. It's too bad. And IF2 goes down really fast from CT4. You can see here. And in all these experimental tests, the IBPF performance equally well, or sometimes it's better than the true parameter. So now it's kind of interesting. How can our algorithm outperform the true value? The reason is that we are considering a high-dimensional optimization problem. The value generated this problem may not be the optimizer of it. That's the point. So we said just that the IENK performance is really bad. How bad it is? So this plot, this table showed it. So here is negative 97,124. So it's a very low, very small value. And our result is here is negative 4,970. And with the IBPF metric, but IBPF with the ENKF metric, so this is negative 4,929. So it's much bigger than this one. So that's why it cannot be drawn on the same plot. Also, this table showed that all these algorithms, all these 3 ones, has almost the same, in the same range of time spent. Here we can see in the first replicate, I tried this in several times. The first one is taking like 15 hours, 78 minutes. And the IF2 is 17 hours, 44 minutes, 0.44 hours, I should say. And the IBPF indeed takes longer time, but basically still in the same range, not that more, that much more, like that. Basically in the same range of time spent. The last one is interesting because it's analyzed the block effect. So people wonder how is the block size affect the the algorithm performance. So in the most challenging case, we firstly on the x-axis is iteration. We want to show is as iteration goes high, as we keep running this algorithm, the algorithm will provide you with better results, the convergence result, better convergence results. And it for each line, it gives the block size. For example, 4, block size 4, which means there are 4 cities in the block. And if 3, there are 3 cities in the block. If just 1, which means just each one works on its own, like that. We can see in this test, just in this test, we can see it's the smaller the block size, it's the smaller, the higher the log likelihood generated. So the kind of better performance with the smaller block size in this analysis. So next is the theoretical performance guarantee. As a statistician, we want to provide the performance guarantee. That is one thing different us to the computer scientist. As we all know, the some machine learning or deep learning, they are to computer scientists is purely like a black box. It works well, but people do not really understand why it works well. But for this algorithm, we have the strong theoretical performance guarantee. So we consider a true joint nonlinear filter because it's a nonlinear model and this is a nonlinear filter. So the pi n A is defined as the value of the latent state and the value of the Markov chain for parameter learning. Given all your data, the probability on that. So this is called a joint nonlinear filter. So this is a filtering problem. This nonlinear filter involves as follows. Firstly, prediction with the prediction operator. Next, correction with the correction operator. So the prediction operator, this is we highly use this operator theory. So here is the one step move up of the dynamics of the latent state and the Markov chain for parameters. So this is the prediction operator. Correction operator is as our data comes in, the yn. So we generated the likelihood and then divide by the marginalized values of yn to be considered to be conditional on yn. So this is the Bayesian learning. So as my data comes in, I correct my prediction. We also introduce an intermediate joint nonlinear filter. Because our model is, we want to approximate using the IBPF algorithm to approximate the nonlinear filter. We feel it quite challenging. So it's very normal in mathematics and theoretical statistics that we introduce an intermediate step. That comes the nonlinear filter pi2. Pi2 is we add on the block correction with the blocking operator. So here is I have the prediction and block-wise the correction. Block correction is my data comes in and each block predict, each block update on its own, each block. The IBPF, based on that, is one additional sampling algorithm because we have the resampling based on the block-wise the weight. So this is that comes the sampling operator here. So based on this block-wise algorithm, my metric, I define the distance. The distance also needed to be block-wise. So here I consider it's a block-wise measure, metric. This metric is based on 2 random measures. So it's a random measure because there's a sampling involved, stochastic sampling involved. This random measure is worked on the family of functions. This family of function is as long as the value of z key, this is the value in the block key, or it's just a set key, equal to the value in another value in this block key. As long as these 2 values are the same, the function is the same. So it's like a localized function family. So my matrix defined on this kind of families, and it's taking it's like a L2 sense. First, they taking square expectation, and then it's taking square root, then taking the soup over this kind of functions. So we can see if there is a deterministic, so this can be seen as the block-wise total variation distance. So if I consider all the functions of if the key choosing to be all the graph, so this is simply is in deterministic setting. So this will be totally the total variation distance. With the localized metric, I also need the localized assumptions. For this assumption is called the localized version of the standard mixing assumption. Mixing assumption is to ensure the ergodicity of the stochastic process, to make the converge as time goes by. So this one is I assume the transition, the density of the yn given xn is 2-sided bounded. And also the transition density of xn and theta n is also 2-sided bounded. Here epsilon is a value in 0 to 1. So this one on the right hand side is above 1. It's more than 1, bigger than 1 for each vertex. And the theoretical result is you under this localized version of the standard mixing assumption. Under this also is the sufficient conditions. We can show that for each block in the partition and a set in this block with this localized metric, we can show the algorithmic error can be bounded by these 2 sides. Firstly, it's the pi n. This is a true filter, no algorithm involved. And then this is the intermediate filter. Here is only the block partition involved, still no algorithm. So this can be said as the bias. This bias is only caused by the block partition. So this term is totally no stochastic. The second term is based on this intermediate filter and my algorithm generated filter. This is the variation part because there is a stochastic sampling involved. We can show this. The algorithmic error can be bounded by this is the cardinality of this size of set. So this means how many numbers of vertex in this set. So it's not the dimension of the whole graph. It's just based on one set only. And divided by some constant, and all the else are some localized quantities, like how many vertex interact with this vertex and how many interact with this block, like these local quantities, no global ones anymore. When we showed this kind of beating the curse dimensionality, we means it's based on the dimension of a local set, not the dimension of the graph anymore. So in this case, in this sense, we can show it beats the curse dimensionality. When we prove that, the proof technique, I just quickly go through it. We use the technique is the decay correlations property. It arises in statistical physics in regards of the investigation of the high dimensional networks. This kind of technique I already used in some of my earlier works. Here, it means that the DOC means the effect on the attribution of a block key of a perturbation made in another block decay rapidly in the distance. For example, currently I live in Texas. The effect, something happened here, I got COVID. So this effect will decrease as the distance you are away from me, like that. And we use the technique it's called Bootstrap comparison principle, theorem, also called some literature call it Bootstrap comparison principle. So this is, let me just intuitively explain this to you. So this is to analyze the decay of correlation property. Not only that, it also can measure the indirect effect. For example, I have the interaction with Edward, and Edward has interaction with you, but I do not have a direct interaction with you. So this theorem can help you do the conduct a cumulative analysis of these interactions. By firstly, I interact with somebody else, and then somebody else interact with you. This is indirect effect. Another technique is, this technique is used in bounding the variance. Bounding the variance, remember I introduced one intermediate filter. This intermediate filter is just for the mathematical pleasure. It's just to help you with the mathematical derivation. But if you want to interpret it, that will be a big issue because it cannot be interpreted as a conditional probability. That's one issue. But we really need to do that because we want to use the Markov random field properties to handle these interactions by spatial interaction and time interaction, and also the recursive of the algorithm. If we want to do that, one technique is called the computation tree technique. So this is quite similar to the belief propagation technique. The belief propagation in BP is by Michael Jordan and his co-author published in machine learning. This BP algorithm is widely used, and the computational tree technique is quite similar. So this technique is really used in this literature by the authors of the block particle filter algorithm, Rabsky and Van Handel. They creatively used this technique to handle this, to bounding the variance. And mathematically, to show that how the computational tree looks like mathematically, it's by this. This products over each blocks of each neighborhood interaction of blocks, like that. And in this work, in bounding all this error, we heavily used the operator theory. And next is to mention is MLE. This is the last topic I want to mention. So each M iteration of the data cloning technique corresponds to an operator, the T sigma. Sigma is the standard deviation of the transition probability density of the Markov chain for theta. And we index the T sigma here as operator based on theta. This applies to a function G. This data cloning procedure can be mathematically expressed as this formula, this ratio. Okay. And the G means and the TG approximate the initial and the final density of the parameter swarm, because we are working in the particle setting. Particle, you can see, it's like a Monte Carlo. It's a swarm. Where this the first one, as I recall you, this is the transition density for theta, and the next one is the extended likelihood function for theta. Okay. And our algorithm is the approximation of this operator, which is the M iteration of the T sigma. So T sigma M is the M's iteration. To obtain its MLE, firstly, we need to show that this operator applied to G. As M goes to the iteration goes to infinity, M goes to infinity, the limiting function exists for every fixed sigma being positive. Then we need to show that as the noise intensity, the sigma goes to 0, noise intensity becomes quite small. This function, the limiting function G sigma, approaches a point mass if the MLE, if it exists. So that means for each iteration, we do not use the same sigma. We let the variation keep goes down in order to find the MLE. And the last, we show that when the number of particles and the number of iterations becomes big, like go to infinity, the algorithm numerically can approximate G sigma. After achieving these 3 goals, we obtain the MLE of the algorithm. Okay. So that is what we want to cover on today. The rest is some references. And so that's all for today. Thank you.
Thank you so much, Patricia. That was wonderful. So I'll stop the recording now, and then we'll move to Q&A.
Okay, great. Should I